Your agent passes all its tests, but does it answer correctly? Welcome to AI Agents in Depth, Episode 6, Evaluating Agents. Build a measurement harness that proves your agent is actually improving, not just guessing. Last episode's read file, edit file, and run command built a coding agent that actually runs code. But does it answer correctly? Open Chapter 6 of AI Agents in Depth by Boji Lai. It's our source of truth every episode. That's the Chapter 6 page, right in VS Code. You cannot improve what you cannot measure. A pass rate makes that concrete. Version B scored 0. 87, version A scored 0. 73. Now see how that principle maps to 4 concrete stages. You're looking at an Excalibur diagram, 4 boxes, right in VS Code. Start at the left. Task sends a task string to run agent. Run agent returns an answer. Judge scores that answer 0 or 1. Those scores add up to the pass rate. 4 boxes, 3 arrows, 1 pipeline. Your tests all pass right now. That doesn't mean your agent answers correctly. Unit tests verify mechanics. Eval tasks verify correctness. These 2 things are completely independent. An agent can pass every test here and still score 0 on real eval tasks. The tests use a fake LLM that always returns the right answer. Pause the video here. The diagram is back, and you're going to trace each arrow. Four boxes on screen. Trace them left to right. Go ahead, try it. Task string in, answer back, score of 0 or 1, then the pass rate, a decimal between 0 and 1, like 0. 67. Programmers call that decimal a float. 4 stages. You'll build all of them next. Section 6. 2. Evaluation environment design sets the core rule. Every eval task must be objective and verifiable. Our Eval Harness builds on every prior episode. Objective and verifiable means the answer is checkable by machine, a number we can assert, not a judgment call. That is the rule the next few lines follow. At the very bottom of agent, Pi, after the EP5 comment, we add the Eval Harness. 3 tasks first. Each dictionary has 2 keys. Input, the question you send the agent, and expected, the exact number the correct answer must contain. An integer is ground truth. No human needed to verify it. Creative writing fails section 6. 2. Only a human can score it. The judge must be independent of the agent. Section 6. 3 is explicit. The same model grading itself has systematic bias. Read it. If the expected number appears in the answer, return 1, pass. Otherwise, return 0, fail. Containment beats equality. Agents phrase answers differently, but the number is always there. A stub is a fake stand-in. We use one here so every take is identical instead of calling a real judge model. Call judge directly in the terminal. You'll see 1 then 0. Proof it discriminates. One then 0. Correct answer passes, wrong expected fails. That's discriminability. A harness that always returns 1 gives false confidence. It's worse than no harness at all. Your turn. Call judge with the third task's expected value. Pause and try it on your screen. Now swap the expected string to something wrong and run it again. Watch the score flip from 1 to 0. The agent code stays completely untouched. We add a measurement layer on top. The tasks list and judge function from last milestone are right here. Evaluate goes below them, wrapping the agent loop from outside, measuring it without touching a single line. The LLM parameter defaults to the fake LLM stub. Never hard-code it. That's what makes your harness testable. For each task, run the agent, score the answer, that's the whole loop. Pass a different LLM, and you're measuring a different brain, without touching the agent code at all. Section 6. 4 defines pass rate, correct count divided by total tasks. Here's that formula. The fraction, 3 out of 3, is more readable on your screen than a decimal. The percentage in parentheses is the production dashboard form. Both land in one print line. Run it. The stub is deterministic. It's the same score every take. Pass rate, 3 out of 3. Gaia, SWE Bench, OS World, Tau2 Bench all use this same structure. 3 tasks is a demo. 1 flip is a 33-point swing. Your turn. Click into the terminal and run it yourself, right now. Same output every time. That's the point of a deterministic harness. A harness that always passes is worse than no harness. It gives false confidence while real failures hide. Open the test file. We'll prove the judge itself discriminates, not just that it runs. The EP01-05 tests are here. They verify mechanics. What's missing is tests for the evaluator itself. Section 6. 4 calls this discriminability, score a wrong answer differently from a right one. 2 assertions. 1 correct answer scores 1, 1 wrong expected scores 0. That's the proof. If both pass, the judge provably discriminates. That's the meta step, testing the tester, not just the agent. A judge that always returns, one hides every failure. Now prove the full harness. A broken agent that always returns wrong must score 0 out of 3. That lambda never gets anything right. Sum must be 0. 3 tasks is a demo. A real eval suite needs dozens before a 1-point gain means anything. That's section 6. 4. Your turn. Run the full suite now. Python m pytest q. Ten tests, all green. The judge discriminates, the harness catches broken agents, and you've proven the eval layer works from every angle. You defined a verifiable task dataset, input plus expected answer, checkable by code. You built evaluate, on top of run agent, without touching the agent itself. You wrote judge as a pure string match stand-in for an LLM judge, and you proved it discriminates with pytest. Correct answers score 1, wrong expected values score 0. Pause here and try this. Add a fourth entry to tasks with input count words in. A B, C, D, E, F, and expected value 6. Run evaluate in the terminal, and confirm your pass rate climbs to 4 out of 4. Quick check. What does judge? Return when the expected string appears in the agent's answer. 1. A passing score. And why must the judge be independent of the agent model? A model grading its own output is systematically biased toward its own answers. The judge must be a separate system. 3 tasks is enough to show the loop. Scale to dozens before you trust a 1-point gain. Next up, Episode 7, Model Post-Training Explained. Follow so you don't miss it.